Hello everyone, thanks for tuning in to my presentation. I'm going to discuss some of my thesis research. I examined the diurnal roost selection of the tricolored bat in Middle Tennessee, and additionally I'm going to compare the use of logistic and probit regression. First, a brief introduction. White nose syndrome is devastating populations of susceptible bats in eastern North America. I'm sure many of you have heard of this disease. It's caused by the introduced fungal pathogen Pseudogymnascus destructans, or PD for short. And species of cave hibernating bats have varying degrees of susceptibility to the disease. Tricolored bats in Tennessee have a higher mean fungal load of PD through the winter than other cave hibernating species. So more pathogen can lead to more disease, which in turn can lead to high rates of mortality. And tricolored bat populations are in decline. In Tennessee, tricolored bat observations in many hibernacula have declined by over 90%. And in 2016, the U.S. Fish and Wildlife Service was petitioned to protect the tricolored bat under the Endangered Species Act. And with these regulatory decisions pending, we really need more studies on the roost selection of tricolored bats to make well-informed regulatory decisions. So what do we know about the diurnal roost of tricolored bats in the summer? Well, the species often roosts in clumps of dead leaves, and often these are dead oak leaves, much like in the picture to the right. And this is unique amongst eastern North American bats. Most species select roost under bark on trees, especially dead trees with sloughing bark. And lasiurans, the genus Lasiurus, they often select roost in live leaves. So tricolored bats are a bit unique in this regard. And additionally, forest stand characteristics and the proximity to features on the landscape can influence roost selection. In Arkansas, these forest stand characteristics were important to roost selection. Tricolored bats selected stands with more large pines, more mid-story hardwoods, and lower canopy cover. However, in North Carolina, it was the proximity to landscape features that influenced roost selection of tricolored bats. So, tricolored bats selected sites further from the forest edge, with a greater density of streams, and at a lower elevation. So we really need more studies on roost selection to determine how much geographic variation exists in roost selection for tricolored bats. So therein lies my research objectives. I want to model stand and landscape level predictor variables to determine which best predict roost selection. For the models, I'll use roost tree or random tree as the binomial dependent variable. And with a binomial dependent variable like this, there are really two options to use for regression, either logistic or probit. So I want to compare these two methods and determine if they yield different results in model selection. So first I want to go into my methods for my research. So first we captured tricolored bats in mist nets, and we glued on tiny radio transmitters, and we used telemetry equipment to track them to their diurnal roost trees. At these roost trees, we tried to confirm the exact location of the roost, and when we were able to do that, we collected stand level variables, 4 stand level variables. So we formed a 0.1 hectare plot centered on the roost tree and measured or recorded variables that may influence roost selection. And we compared these variables to the same variables of random trees that were determined by walking a random distance between 50 and 100 meters at a random bearing to the nearest tree over 10 centimeters diameter at breast height, or DBH. And here are the stand scale predictor variables that I used. You can see that 3 variables were removed from the models because they were collinear with some other variables. But just to give a few examples, I estimated the overstory canopy closure, the basal area of the stand. We counted the number of trees greater than 25 centimeters DBH in the plot, etc. Next, I want to talk about the landscape scale predictor variables. So at each roost tree, whether it was visually confirmed or not, we collected a geographic coordinate. And so I entered all of those into ArcMap 10.3, and then I measured the distance to or the density of features on the landscape that may influence roost selection. And I compared these to the same variables of random points on the landscape level, but I selected these random points a little differently. First, I determined the center of all the documented roost trees, and that's indicated by the red X on the map. And then I buffered that center point with a radius, the farthest distance any one bat flies while foraging. And that ended up being 24.4 kilometers. And then I plotted random points in forest within the buffer. So for this, we're assuming that all the forests within that greatest distance any one bat flies are available for roosting. And here are the landscape scale predictor variables. You can see that distance to the nearest water body, distance to water, was removed because it was collinear with distance to the intersect of the Eastern Highland Rim and Cumberland Escarpment physiographic regions. All the units for these variables are in meters. And just a few examples, we used roost tree elevation, density of forest, and a 452 meter buffer, distance to the nearest stream, etc. Now I want to discuss a little bit about logistic and probit regression. I'm sure many of you have heard of logistic regression. I think in ecological studies we see this method a lot, but additionally there is probit regression, and that simply stands for probability plus unit. Both methods use maximum likelihood estimation to estimate the parameters of the model, and this is just opposed to ordinary least squares like used in linear regression. But the main difference lies in the assumption of the distribution of the error terms. In logistic regression, it assumes a cumulative distribution function of the logistic distribution, and then probit uses the cumulative distribution function of the standard normal distribution. So what does this mean? I think it's easier to understand by looking at it graphically. So on the left is the logistic distribution, or specifically the cumulative distribution function of the logistic distribution, and on the right is the normal distribution. So you can see at around the probability of 0.5 in the middle of the y-axis, the regression lines are really similar. But as you reach the tails, you can tell that the logistic distribution has longer tails. That is, it approaches values of 0 or 1 on the y-axis a bit slower than the standard normal distribution. Next, I wanted to look at these regression lines with real data, with some of my data, to compare the differences and to look at them graphically. I had a bit of trouble plotting these regression lines, so I wanted to provide and show you my code and how I did this. So I'll just briefly go through this. You may need to pause it if you want to use this in future work, I guess. So first, I ran a general linear model named intersect, or intersect_p. Here, roost tree is my binomial dependent variable, so 0 for a random tree and 1 for a roost tree. And then my predictor variable here that I used for this graph is distance to the intersect. And the only difference between these two general linear models is in the link function within the binomial family. We used logit and probit. Next, I plotted distance to the intersect on the x-axis and the values of y, either roost tree or random, on the y-axis. And I labeled the y and x. Next, I used the predict function to insert the logistic and the probit regression line on the graph. Next, I added the fitted values along the regression line for both the probit and logit. Added a legend and a title. And this is what we end up with. So again, the y-axis is the probability of roost selection, and the x-axis is distance to the intersect of the escarpment or highland rim. And the red line is the logistic regression curve, and the blue line is the probit curve. And you can see At around 2,000 meters from the intersect, the lines are essentially the same, but as you move toward the tail, at around 6,000, 9,000 meters, you see that these lines diverge a little bit. So that's the main difference between these two methods. And here I should point out that probability of roost selection and distance to the intersect have a negative relationship. So as the distance from the intersect goes up, the probability of selection goes down. So also plotted density of streams. I used the same code, just a different predictor variable. And again, we can see toward the middle of the regression line, they're essentially the same, logit and probit. But as you reach the tails, the lines diverge a little bit. And probability of roost selection and density of streams here has a positive relationship. So as the density of streams increases, the probability of roost selection also increases. So the other difference between these two regression methods is interpretation of the coefficients. In logistic regression, the coefficients are the natural log of the odds ratio. Therefore, you can exponentiate the coefficients and get an odds ratio. For example, if you had a coefficient of 1.5, you would exponentiate it and get an odds ratio of 4.48. So for every 1 unit increase in x, the likelihood that y equals 1 would increase by a factor of 4.48. In other words, for that 1 unit increase in x, you're 4.5 times more likely that y would equal 4.5. So this is really intuitive, and it's one of the major benefits of using logistic regression. Probit regression takes a little bit different of an approach. The coefficients here are z-scores from the cumulative distribution function of the normal distribution. And so back to our example, if for every 1 unit increase in x, the likelihood that y equals 0 would increase by a factor, or by a z-score of 1.5. So then you would take that z-score to a chart, and you would determine what probability is related to that coefficient. So you would use the z-score to get how much the probability would increase for every 1 unit increase in x. So it's a little less intuitive, but it's still a good method. You would expect to have the same results. Next I'm going to move into my results. So my code for the general linear models, for the global models, are at the top. And again, I just want to mention that my dependent variable here is binomial. It's roost tree, so it can take either a value of 0 for random or 1 for roost tree. And then all my predictor variables are in the model. And I used either the link logit or probit to get the two different summaries here. And so just looking at these summaries, the p-values are pretty close for both of them. However, they're not exactly the same. There's a little bit of difference here, but not a lot. So next I want to look at model selection. To do this, I use the package multi-model inference in R, and I follow the methods outlined by Burnham and Anderson 2002, and I'm just going to briefly run through this code. So the first thing is the options in a fail. So I just tell an R to fail if there's a missing value. And next I use the dredge function, which is in this multi-model inference package, to run all possible models. So where I have underlined in this code is the model, and for this I use the global model using logit and the global model using probit. And additionally I added the adjusted R-square, and I limited my predictor variables in each model to 3 because I didn't want to run into problems with overfitting the model, so I limited them to 3 predictor variables. Next, I ranked the models based on AIC values, so from lowest AIC to the highest. And then I subset those models and with a delta of less than 2. So I only want models with an AIC less than 2 from the model with the lowest AIC. And so I'll consider these models potential or plausible models. Hopefully that made sense. And so here are the results. The first thing that sticks out here is that the most likely model is the null model, and so it has no predictor variables at all. And then if you go through and look at the other models, the other plausible models, you can see for both Logit and Probit, they are the same. And so there was no difference in model selection at this spatial scale, at the stand scale. Also, just look at the adjusted R-squared here. The model fit is not very good. That is, these predictor variables don't explain much of the variation in roost tree selection. But the two methods did result in the same models. So next, let's look at the landscape scale models. Again, I ran the same, or essentially the same code in R. Here I have roost tree as the dependent variable and all the possible predictor variables at the landscape scale, and I used either the Logit or Probit link, and I ran the summary. So I want to point out here that our p-values for the variables distance to the nearest stream and density of streams are different. So for the Probit p-value, these variables are significant at the 0.05 level, but in the Logit model they are not significant at 0.05. So if you were just looking at p-values and significance, you may interpret the results of these models a little bit differently. Next, I want to look at the results from the model selection at the landscape scale. And again, the code is exactly the same. And again, I get the same model, so there was no difference in model selection. And at this scale, I'd like for you to look at the adjusted R-squared. You can see that this was a much better model fit, in that these landscape scale predictor variables explained about 80% of the variation in roost selection. And the variables that were in these models are density of streams, distance to the intersect of the Highland Rim and Cumberland Escarpment, and density of streams. So in conclusion, the Probit and the Logit models differed in the p-values for some of the predictor variables, but for model selection, the plausible candidate models were ranked identically. There were some differences in the AIC values and slight differences in the AIC weights, but it really didn't make much of a difference. Now I just want to give a few conclusions about the research itself. The stand scale predictors in the models were not good predictors of roost selection by male tricolored bats, as we only had males in our samples. And a likely explanation for this is that the forests in our study area are homogeneous. They're pretty much the same. There's not a lot of variation. So if tricolored bats are selecting this area, you know, the forest is essentially the same regardless of where they roost. And O'Keefe et al. 2009 had a similar result in their study area in North Carolina, and this is the explanation that they provided. And I concur. I believe that it's a pretty good explanation of why these stand scale predictors are not important in our study area. But the landscape model was a good fit. And here tricolored bats selected sites on the landscape in close proximity to the intersect of the Plateau Escarpment and the Eastern Highland Rim. They selected sites closer to streams and areas with a higher density of streams. Along the Cumberland Escarpment, there's a lot of caves and there's a lot of karst features. So these male tricolored bats could be roosting near their winter hibernacula, and this would be a similar behavior to male Indiana bats. And streams are important as foraging areas and also as corridors for tricolored bats. And we think that the tricolored bats could be foraging near these streams where they roost to, but also they're probably following these streams as corridors to larger bodies of water, where in other aspects of my research we found that they tended to select for foraging. Here's some literature that I cited, and if you have any questions, feel free to send me an email. Thanks again for tuning in.